Is it 13, 14? Or is it 13?
12, 13.
12, 13, okay. Okay, thank you. Alright guys, so we start with one. This is exam. Alright, this is exam 2012-13 question 1 part 4. So you are told that alright, you are told that you have n independent IID random variables with the CDF given by this. And the question in part 4, question 1, is to find the distribution of find the distribution of the maximum. Okay, so what do? You start with the statement, we want to find the distribution of the maximum we need to find the CDF of it, right? So the CDF is the probability that the max of x1 to xn is less than or equal to some number, let's call it z, right? Now if the max is less, then this implies that each if the maximum is less than or equal to z, then each x has to be less than or equal to z. And because of independence, guys, so using independence, we can write this as right, that's using independence. Now we know that each of these guys, this is equal to f at z, and this is also equal to f at z, right? So what you have is the nth power of fz, right? Now we know that fz is given by this formula here, right? So I'm going to sub that in here. So this is going to be this. Now you should power this to n. What do you get, guys? This will become the n over here will come over here. Do you follow that, guys? Yes. Okay, now I'm gonna, in place of n, I'm gonna apply the following trick. We can write n here as follows: e of log do you see what I've done? I have replaced n by e of log of n. Same, right? Now because you have two e's, you can combine them into one. You can write this as log of n minus z. Yes, and finally, not yet finally, let's you can write this as sigma log of n minus z minus plus mu divided by sigma. And finally, this is the final step, you can write this as, if you pull out a minus outside, then it will become z minus mu plus sigma log of n divided by sigma. Right now, so this is the final form I'm getting. Now, if you compare this, the only difference between this and the stuff that we started off with, this one, the only difference between this one and this one is that in place of mu, we have mu plus sigma log n. So this, what you have here is the CDF of Gumbel with mu replaced by mu plus sigma log of n, right? Okay, do you see that, guys, or no? Yes? Huh? No? So what you have here, guys, is the same as the Gumbel CDF, or the CDF of the Gumbel distribution. With mu, in place of mu, you have mu plus sigma log n. So therefore, the conclusion is that the max of x1 to xn must have a Gumbel distribution with mu replaced by mu plus sigma log n. Yeah? Is it the question you asked, guys? I hope this is clear. If not, give me a shout. If not, just... Alright, other questions, guys? I'm sure you only have like 2 weeks, exactly 2 weeks from today. I heard some of you had a test today in the morning. Did you?
Yes.
How did it go? Okay. Not bad. Last night. Any other questions, guys? I'm sure you guys have questions. Yes. Yeah. Many more, yeah. You only need to remember the 3. Yeah. Yes. Yeah, you don't need to remember the rejection rate. So only these, just, yeah. Any other questions, guys? How is it? Do you have questions? You want to ask me now? No? What about you? Okay. You have any questions? Yeah, okay, good. Yes. Yeah, I just made a substitution. I just put y exactly equal to y divided by theta. So it should be, this one should be exact. So I divided y by theta.
Yeah, but it needs.
Yeah. Yeah. You should get the same answer, yeah. Guys, yeah, please ask me some questions, guys. I mean, I send you guys the office hours, so I'll be in my office until 23rd of May this month. I send you the times I'll be in my office, right? You got my email, right? Yes, yes. You can drop in and see me. Oh, you can also send me an email anytime, 24/7. Okay. What about you? Have questions? What now? What about you guys? You have questions? Jojo? Oh, you want me to do now? I don't know how to check it. It's difficult for me to say now. I need to check it. Yeah, I need to check my answer. I don't know. What else did I get? I got. You got your pronouncers? And let's see. Yeah, the bias is 0. So it must be the same as the variance. The variance is, what is the variance here? Is I don't know. It's really difficult to see this out actually. It's 3, yeah. But if you multiply by 3, there's a 3 outside. So it has to be 9, yeah. Because you need to compute the variance from these two, right? So can I use your pen? You need to compute the variance, which is delta squared by 3. Yeah, that's this one. Yeah, you need to compute the variance. Yeah. Yes. If you can get the rejection rule by using the NP llama, then that means it's most powerful. Otherwise, it's not most powerful. Like you should derive the rejection rule by using the NP llama. Remember, I did several questions on how to use the NP llama. Yeah. So you can derive the rejection rule for this hypothesis using the NP llama. Then that means the test is most powerful. Yeah. This one most powerful. Yeah, that's okay. Yeah. I use it. Well, you need to use the You need to use this part to answer the question, part C. No, you need to use part C. Part C is this one, right? This one, yeah. So that from this you can see that the distribution so it's look like you have n lambda in place of lambda, and I'm not sure whether you got this right. Yeah, you have n lambda. So in place of lambda you have n lambda, and in place no, I mean you need to compare this. This is the MGF of the inverse Gaussian distribution, and you need to compare this one with this one and see what kind of distribution Y has. Okay, so because yeah, you're right. Yeah, so you can write this as this, right? You can write this in this form. Now you can see that this, you can compare this one with this one, right? And you can see in place of mu you have n mu, and in place of lambda you have n squared lambda. So and you should compare this formula with this one. Yeah, that's what I'm saying. In place of lambda you have n squared lambda, and in place of mu you have n mu. Okay, so the distribution of y is inverse Gaussian with the parameters lambda replaced by m squared lambda and mu replaced by n mu. You follow what I'm saying? No, but probably you can't, because we have to match this with this one. We have to match. That's why it's important to write this step. Because this, when you write it like this, you can see that one-to-one matching between this formula and this formula. Yeah, because you see that wherever there's lambda here, you have n squared lambda, and wherever there's a mu here, you have n mu. Yeah. So this corresponds to an inverse Gaussian distribution with lambda replaced by n squared lambda, mu replaced by n mu. Think about it. Yeah, think about it. Just you need to compare this with this one. You guys okay? How you doing? Any questions with that one? You want me to do? Oh, you want to do it to me now? Okay, thank you. What about you? So, do you have any questions you want me to do? No. You have any questions? You want me to do? Thank you. Thanks. Hello, sir. Do you have any questions you want me to do now? Okay.
Is that on the
But this is here somewhere. Where's that initiative? Somewhere over there.
Yes.
So you have it. Yeah.
Should I sign both, please?
No, just one. Just one. Okay. Do you have any more questions? I mean, it's really important that you do. I mean, just try to do as many of the past exam papers as you can. I mean, we have the last 10 years exam papers with solutions, so try to go through all of that without looking at the solutions, and you'll be fine. I think you can do it. Yeah. Anything you want me to do? You want? You don't have questions? No, it's only if it is integers, negative negative integers, and also when a equals to 0, this is 0 or negative integer. In other places, we will define the order of all
Could you go over how to find Emily Corbin's? So it's on the 2012 email, 3 part 3.
Okay. Part 3, 2000.
12, yeah. Oh, was it 2012? Yeah, 12.
Okay.
3 part 3.
Thank you. Alright guys, this is exam Could you guys listen please? I think in this question you are given two two random variables. So x has the normal distribution, y also has the normal distribution with different parameters, and they are of course independent of each other. Now in part 3 of this question you are asked to find the correct me if I'm wrong, but I think the question is to find the MLE of the probability x greater than y, or x less than y or greater than y, doesn't matter. Okay, so to do that what you need to realize is that that the probability that x greater than y or x less than y is the probability that x minus y is less than 0. Yeah, this is the probability that Yes? Right, now you have a difference of two independent normal variables. And one of the properties that we learned in week 1 of this course is that if you take linear combinations of independent, then the linear combination is also normal. Right, so in this case, the differences of two normal variables is normal with parameters do you see how I got from this to this, guys? So this is stuff we did in week 1 of this course, guys, right? Yeah, you remember or no? Okay. Now the next thing I'm going to do is I'm going to standardize both sides. I'm sure you know what I mean by standardization. Standardization means you subtract the mean and divide by the standard deviation, right? So I'll do that on both sides. So I'm going to subtract the mean, which is mu x minus mu y, and divide by the standard deviation, which is the square root of 2 sigma squared. So do the same thing on the left and the right. Yeah? Okay, guys? Alright, now what you have on the left is the standard normal variable n01, and what you have on the right is mu y minus mu x divided by root 2 sigma. Alright, so this becomes simply phi. Capital Phi is the CDF of n01 at mu y minus mu x. Yeah. All right. So this is the first thing you should do. Now the next thing, so what this implies is that the MLE for the probability that x is less than y, which I denote by this. So when I put a big hat, it represents the MLE. It's gonna be phi I think I'm assuming sigma is known. So the only is that right? Is the question? Does the question says that sigma is known? I can't remember.
Yeah.
It does. Okay, thank you. All right. So the MLE of this is equal to this. Now, so the only thing you need to find is the MLE of this, and if you do the first two parts of the question 3, you will see that mu hat y is simply y bar, and mu hat x is x bar. All right. So y bar is a sample mean of a random sample on y, and similarly x bar is a sample mean for a random sample on x. So this here is the MLE for the probability that x less than y. Okay, guys? Yeah. I'm happy to do more questions if you have. Yeah, one thing I want to say is that we did a lot of rejection rules in the latter part of the course, and there are only 3 rules that you need to remember for the exam, and the 3 rules are in the formula sheet I gave you, or it's on the website. The other rejection rules will not come. Okay, so you don't need to worry about all the other rejection rules that we talked about in the latter part of the course. You understand what I'm talking about? So, but there are only 3 rejection rules that will come in the text. That's checking. Okay. And those rules are in the formula sheet on the course website. Yes. Sorry, sir. Sorry.
It's just a question.
Oh yes, yes, yeah, sorry, I should be. Yeah, it's wrong, yeah.
So you know you're not going to that's right.
Yeah, you're right, yeah, thank you, yeah.
It's in your
Okay, so I'm not correct, sir, you have questions you want me to do? Okay.
Yeah. I was going to ask you a question.
Any other questions you have?
Not in a minute, but I'll tell you.
What is it? All right, guys, I've got one more question. All right. I think this is exam 2011, maybe 2011-12, I guess. I may be wrong, but so basically you have all right. Can you guys listen, please? So you have this equation that yi is equal to beta xi plus ei. Ei are IID normal with these parameters. Sigma squared is known. Xi's are fixed numbers. So the only parameter that is unknown is beta, and we want to find the MLE of beta. Right, so the first thing you should figure out is what is the distribution of EI are normal with these parameters, okay? And beta is a parameter. Beta is a parameter. Xi is a fixed number. So what distribution will this have, guys? Yeah, you're adding a constant to this, so it will be normal with parameters. All right. you follow what I've done, right? Because this is a fixed thing, right? And you're adding a constant to a normal variable, so it becomes another normal variable with parameters this and this. Yeah, right. So the first thing you should do is to write down the likelihood is going to be the product of the PDF of the observations. The observations here are yi, and each yi has this distribution, right? So it's going to be the product yeah. So what I have written here is the product of the density of this normal distribution, right? Now if you simplify it, once again please make sure you simplify things correctly, because if you mess this step, then everything else will be messed up. Okay, so this is, after simplification, this is what you should get. This simplifies to this. Okay, now the next step is to take the log of the likelihood of beta. So it's the log of this. Okay, and the next step, we have only one parameter, so we just differentiate the log with respect to the parameter which is beta. Now this, so when you differentiate, you get you get 2 times okay, this is what you should get when you differentiate with respect to beta, right? And this, after simplification, the 2 and the 2 will go, so the 2 and the 2 cancel out, the minus and the minus cancels out, so you get 1 over sigma squared times the sum all right. So this is what you get, right? Now we're gonna set this to 0, and we're gonna solve this equation for beta, right? So setting this to 0 implies that the sum of yi xi minus beta xi squared is equal to 0. All right. So this means that the sum equal to 0. So this implies that beta, the solution for beta is equal to equal to this. So this is the solution for beta. Now because the likelihood has only one parameter, you must show that the second order derivative is negative at the MLE, right? So the second order derivative is d2 log by d beta, and this is going to be the first order derivative of this, which is, it's easy to see that this is the second order derivative, and clearly this must be a negative number, right? And hence beta hat is an MLE. Alright? Is that clear, guys? Yeah. And the rest of the question is just to show, is to find the bias and the MSC. I'm sure you can do it. I'm sure you would know how to find the bias and the MSC of beta hat. Shouldn't be difficult, right? Or will it? No. Shouldn't be to find the bias and the MSC of other questions, guys, please. Yes, oh, you want to hand it in? Thank you. Thank you. Other questions, guys, please. Any questions, sir? No. Sir, do you have anything, any question you want me to do?
Well, I'm doing 21 weeks actually at the moment, but I think
Okay.
thank you.
Stay away. Sorry. Yeah.
I just wanted to ask you a question. When you're looking at the geometry distribution, how do you from that step to the next?
That's the geometric series because you know that can I write it?
Yeah.
You should have something like you have something like say a to the power y from 0 to infinity. This is equal to 1 divided by 1 minus a. You know this formula. If absolute value of a is less than 1. This is a famous formula. You've probably seen this before. So that's what I have used here because what I have used is the same is pretty much exponential ty 1 minus theta y from 0 to infinity, which is of this form because what you have is e of t times 1 minus theta, the whole thing raised to the power y. So this is your a. In this case, this is your a. Yeah, so this will become 1 divided by 1 minus e of this a, which is e of t 1 minus theta.
Okay.
Does that yes?
Yes. Thank you.
Next question. You okay? Yeah.
If you've got, sorry, no.
Yeah,
If you've got
so-
if you've got the bias equal to 1, can you just take the estimate
Yeah.
user as delta?
Yeah.
Okay, cool.
Yeah, you're on the right line.
Okay.
Yeah.
Thank you.
I'll see you guys in a minute, okay? Please bring some questions to the hour from 4 to 5. I'm going to walk down to have all of you got your test paper back? Your test? Anybody here hasn't got the test back? Because I'm carrying all this everywhere. This is all full of test papers.